Okay, hello everyone. So today we are going to discuss about PN junction diode. Okay, so in the PN junction diode, the two type doping is done. In the one side there is a P type and another side there is a N type. In the P side, as we all know, the majority carriers is holes and minority carriers is electrons. Suppose here the majority carriers is hole, which is I denoted by PP, which is Na, and minority carriers are electron, which I denoted by Np, which is Ni square by Na, which is the intrinsic carrier concentration. So you can say that Pp is much greater than Np. And similarly, on the N side, the majority carriers are electrons, right? And let's denote it by Nn, and its concentration is Nd. And here the minority carriers is holes. Let's denote it by Pn, which is Ni square by Nd. So as you can see that here the majority carriers is holes and minority carriers is electron and no bias is applied. So you can say that as the majority carriers is holes here, and so here the concentration of hole will be high as compared to this. So holes are tries to diffuse from here, holes will come in this direction, and as the electron concentration is high, electron try to diffuse in this direction, right? Okay, let me clear this thing now. I hope this is clear. So now as the electron move from p side, at the holes is moved from p side to n side, what they leave? They leave negative ions here, and these are immobile ions. And as the electron is moved from n side to p side, they left out positive ions. These are immobile ions. So as the diffusion is happening here, so there will be a diffusion current. Okay, and you can see there is a positive ions and negative ions. So there will be electric field in this direction. So as more diffusion happen, the strength of the electric field will be much more. So due to the electric field, there are minority carriers also. Suppose here the minority carriers is hole, so electric field will force the hole here in this direction and force the electron in this direction. So for this reason there will be a drift current also. So in the equilibrium, what happens? The total drift current is equal to total diffusion current. So as they are in opposite direction, they will cancel each other. So our total current will be zero. So no current will flow when no bias is applied. And here there is a electric field. Okay. Now what is happening here? Now let's look into it in a different way. Now if I plot the charge here, Okay. So as you can see, up to this position there will be positive charge, and here up to this position there will be negative charge. We let consider this xn and xp plus q minus q, and this plus q is how much? The amount of plus q is q times nd. Okay, here nd is per volume, so we have to multiply with the volume. So what is volume? A is the cross sectional area and the length is xn. Okay, this amount of charge is here, and the amount of charge here, we let's take its mod value q na a into xp. Similarly, now if you equate this amount of charge will be same if we take its mod value, because the amount of electron goes from n side to p side, the same amount of holes come from p side to n side and they recombine. Now if we make these two equal, sorry, q nd axn equal to q na axp, we will get a important equation which is nothing but xn by xp is equal to na by nd. Okay, so this is a very important equation. Okay, now let's plot the electric field also here. Now how you determine the electric field? So at the edge of the depletion layer the electric field is zero, no electric field there. Now how we will determine the value of the electric field? Just place a unit positive charge here. So if you place a unit positive charge here, the positive ions will repel it and negative ions will attract it. Okay, so the electric field will be in negative direction, and here its value will be maximum. If you place this here or here, its value will be less as compared to this. I am talking about in negative value, okay, or mod value. Its mod value is maximum. So at this position it will be maximum, and from here to here it will decrease. Okay, and this is Emax. Of course it is in negative minus xp, and this is xn. Okay, now my question is, why electric field is developed? As we know that E is equal to minus dv by dx. So now, due to the change of potential from the distance, there will be electric field. So there is a potential difference from here to here, as you can see. So what is the potential difference? So potential difference can be easily calculated by finding the area here. The area here is how much? This is just a simple triangle. So let's assume omega is equal to, this is the omega, w is the depletion length, depletion layer width or depletion length, xn plus xp. So area will be half into Emax into W. This is nothing but your V naught. So Emax you can also write as 2 V naught by W. So this what happen when no bias is applied here. Now if you look in the band diagram of simple PN junction diode when no bias is applied, okay, let's plot it here. Okay, so this is P, this is N. So let's plot the band diagram here. So as there as we know that dEc by dx is equal to dEv by dx is equal to dEi by dx is equal to q into E net. Okay, so in the neutral P region and the neutral N region there is no electric field, so there will be no bending in the band diagram, but as you can see here there is an electric field in this direction as the depletion layer is created here. Okay, so there will be of course a band diagram, or sorry, there will be of course bending in the band diagram. Okay, and we also know that the bending in the intrinsic Fermi level is Q into E external. As there is no external electric field is applied, there will be no bending in the extrinsic Fermi level on the band diagram, so it remain constant or straight line. So suppose this is my extrinsic Fermi level. Okay, now okay, now you know that in the p-type semiconductor the extrinsic Fermi level lies under the intrinsic Fermi level or above the valence band. So before that, let me draw the reference here. Okay, so our extrinsic Fermi level will lie somewhere around here. Sorry, intrinsic Fermi level lies somewhere around here. Okay, and my valence band, suppose lie somewhere around here. Okay, this is my valence band, lies somewhat around here. Now above this there will be a conduction band somewhat around here. In the similar way, we also know in case of n-type semiconductor, the extrinsic Fermi level lies above the intrinsic Fermi level. Okay, and closer to the conduction band. Okay, now let's plot it. Somewhat around here. Okay, and then plot the valence band somewhat around here. And my conduction band. is here. Now as I already told that there will be bending in band diagram also, right? So as there will be bending in band diagram, in which direction the bending will be there? Okay, as you can see the electric field in this direction, so in this direction, okay, in this direction the bending will be of positive slope. Okay, now let's show it. So in this direction the bending will be of this positive slope. It will be not a straight line. Why this is not? It is not a straight line. The electric field it not constant at every point. Electric field is changing. If electric field is constant at every point, then it will be a straight line, no issue in it. Okay, now similarly there will be bending in conduction band also, sorry, valence band also, the similar way. And in the intrinsic Fermi level also there will be bending. Sorry. Okay, so this is the band diagram will actually look like. So as this is a neutral, there will be no bending, an electric field in this direction, and the potential difference this is V naught. So to electron jump this to this is Q V naught. So Q V naught energy is required to move an electron from uh, this n side conduction band to p side conduction band. Okay, now this is just a basic discussion. We'll move further in our next lecture. So thank you.